So, hi friend, this is Shomik Bishwas. You are attending my class of circuit theory and network, and this is the second class of that active filter. So, today my topic starts with that filter. In the last class I told you what is the image impedance and what is the name of Z0 and what is the name of gamma, what is the propagation constant, what is the characteristic impedance. Lot of things I have just discussed with you. Also, what is the image impedance, what is the condition of symmetry and reciprocity. These things already I have discussed in the two-port network. Again, I have discussed in that the context of image impedance in the concept of characteristic impedance like here. So write that in this today's class we are taking one symmetrical, as you can see it is a symmetrical network, that Z1, Z1 by 2, Z2, these things are given in the form of T network that you can see right here. So I am just taking that characteristics of the filter network, that points to be remembered, that characteristic impedance Z0 what I have calculated, and for T network that is my circuit. This is the image impedance Z0, that is Z in, and this is the symmetrical network of T, so it is Z1 by 2, that is Z1 by 2, and that is Z. So you can easily convert that T network in that form of pi or other Z network by that Z transformation equation. So you have to write in the form of V1 equals to Z11 I1 plus Z12 I2. In this way you have to consider that entire Z network, but right now it is not necessary. We are just considering the T network to evaluate this particular one. So right here, if you are having this particular one, so what is Z in? So here that Z in equals to, if you are seeing from this side, so what is Z in? Z in equals to Z0 equals to here Z1 by 2 with that parallel of this. Now obviously there is a parallel combination, as you can see that here actually like this, you can see this is a parallel combination here, that Z12 and Z0, this is in series with that parallel of Z2, so it is given like this, and Z1 by 2 is series with this, so it is a final impedance structure of Z0. Now if this is a T network and this is a symmetrical network, so from this side if Z0 is there, so that Z in must be equals to again Z0. So finally you can see that in the both side, equating that both side, we will be getting as that Z0 equals to like this. So how to get that? You can easily calculate that particular value, and whatever the Z0 here and here, take it as a common, and finally you will be getting that Z0 equals to this. So this particular Z0 is written as ZOT. So in the previous class I have already shown you that ZOC, it is a open circuit parameter. So if you are making this is open, Z0 if open, so ZOC equals to this and ZSC equals to this. So if you are adding them up, finally you can see this is, if you are making this particular one, Z0 is terminated, so obviously see this particular form here. So if Z0 is terminated, I want to mean this, so the current is flowing only this path, it will never go to this path, it will never go to this path. So obviously it is just Z1 by 2 plus Z2 Z2. Okay, just see, that is again Z1 by 2 into Z2, and here ZSC, that is a short circuit case. So obviously you can see that in the short circuit case, when this particular point Z1 is shorted like, so obviously the current is, after passing to that Z1 by 2, it will taking two paths, one is this and another is this. So obviously what is the final calculation, that Z2 and Z1 by 2, they are in the parallel combination with that series of Z1 by 2. So you can easily take that consideration that ZSC equals to like this and ZOC is like this, that is ZSC, and here it is ZOC. So what is ZOC? Z1 by 2 plus Z2 as I have shown you, and what is ZSC? That is Z1 by 2 with that parallel of this. So by equating we can again write here, we can again write that again there we can write it as ZOC equals to ZOT square by ZSC. At the same way I have shown you that what is the image impedance in the term of 1 and 2. So Z10 and Z1s, if multiplied and root, it should be that ZI1 image impedance. Here it is a OT square. So obviously that Z0 can be characteristics like this. So in the other side we can again consider the same concept for the pi network. If it is a pi network, one T network like here, if converted to the pi network, so it just look like the same structure. You can easily convert one T structure to the pi structure. You can see the problem will be easily evaluated in front of you. So here I have again calculated that Z in, and that Z in here the image impedance. So finally for Z0 pi, for Z0 it is coming like this. If you are again evaluating this particular equation, so obviously Z0 is like this. So that is Z1 by this. Again that Z1 Z2, if you are dividing in this way, you just go back to that previous one, what I have jotted, that Z0 equals to like this. Yes. So if you are just using this, so if you are just dividing this 4, that Z1 by 4 and this is by 4, so obviously these two will be cancelled. So it will be Z2 plus Z1 by 4, and obviously one Z1 will be multiplied with this, so it finally coming like this. So it is Z1 Z2 by ZOT. Okay. Now finally we can conclude that here that Z0 pi by Z0t equals to Z1 Z2. So this is very important equation for that circuit, and that Z0 pi or Z0t equals to the open circuit and short circuit root over. So that is the function already I have discussed to you. So if it is k, so I can again write that k square equals to Z0t Z0 pi. So Z0t and Z0 pi, this is Z1 Z2, so k square equals to Z1 into Z2. Okay. Now come to this propagation constant gamma, what I am talking to you, that here gamma equals to alpha plus j beta, where alpha is the attenuation constant, okay, and beta is something is there in my previous lecture. I didn't discuss it, and I told you in my next lecture class I will tell you that what is the function of beta. So right here that I have again write that gamma can be expressed as alpha plus j beta, and alpha here is the attenuation part and the beta is the phase part. So one signal is transmitted, so obviously some changes are there in its bandwidth, and obviously the amplitude may change, the phase part may change. So that phase part is representing with that beta and the attenuation part is representing with that alpha. So we know that e to the power gamma equals to I1 by I2. So from this equation I can again write what is the value of I1 by I2. Okay. So that is Z1 by 2 plus Z0 plus Z2 and by this Z. So finally you can easily evaluate here that Z0 equals to Z2 into e to the power gamma minus 1 minus Z1 by 2. Now Z0t, this Z0t is also known to you, that is Z1 square by 4 plus Z1 Z2 under root. So just put this value and you will be getting as Z2 e to the power gamma minus 1. So this particular one equals to that Z1 into e to the power gamma, just placing this value, and finally we are getting this equation, as you can see, that is e to the power gamma minus 1, that square, if multiplied with that z2, it will be getting z1 of e to the power gamma. I just put this equation on this, you will be getting simply this. So e to the power gamma plus e to the power minus gamma minus 2 e to the power gamma e to the power minus gamma, so it is just minus 2. So finally it is like this. So it is 2, if you are dividing it by 2, so here it is plus 1, and finally the output is coming as cos h gamma equals to like this, sin h gamma equals to this. So if you are having some sort of doubt on evaluating this cos h gamma and sin of h gamma, you know that cos of h gamma equals to root over of AD. Okay. So for the symmetrical network, A equals to D, so you can easily calculate it out. So what is the representation of that A? What is the representation of D in Z parameter? You just place it right here. You can easily get that what is the expression of cos of h gamma. Now what is the case of sin of h gamma? You can easily calculate it by that value of cos of h gamma, and that is z0 by z2. So in this way you can calculate that different parameter of z1 and z2 in the term of, see it again, in the term of cos of h gamma and sin of h gamma. So if gamma is known to you, and if that z0 it is known to you, z0 is known to you, and that gamma is also known to you, so you can easily convert in the type of ABCD or Z parameters or pi parameters like this. So this type of parametric representation is far more necessary of finding out different parameters when a signal is transmitted, that input impedance, output impedance, that alpha, it means attenuation, the beta, it means the phase constant, the propagation constant, different thing has to be calculated out before making a particular filter. So in the next class I will discuss much more detail on this, so please be with us and follow my lecture classes, and it will be the third lecture when I will be giving much more details on that active filter, and in the end of the session we will do some numerical problems on that active filter also. Thank you very much. See you early next in my next class. Bye bye.